Hey, folks. Hey, folks. Hey, yo. Doing some, just putting things where they belong. Putting things into their place. Placing things. Getting set up. I hope everyone's doing great. Hope you're having a fan-fucking-tastic day. My day has been pretty good so far. Although, I had my caffeine too late because I had a call this morning and now I have a headache. Thank you, drug dependency. Thank you. Today we're going to be hacking on Jank's IR some more. IR, intermediate representation. We are going to do watch and there we go. And then let's see, what else are we getting set up? We had a, I guess, I should show off what I've built. It's been 1 week. It's been 1 week since I have started on Jank's LLVM, or no, Jank's own IR, not LLVM IR, Jank's own IR. It's been 1 week. What can it do? Can it do things? Let's find out. So we have, here's one of the things I was working on recently, looping with recur. All the colors just changed for all of those. That's crazy. I think like LSP kicked in probably. What we have with all of this is we have support for IR generation for functions and loops and ifs and recurs, and here like we're returning a keyword. We have a function call here, a function call here, a couple of literals, bindings, and we get this lovely little output here. It's even syntax highlighted. Jank already had a highlighter for code, which we use for snippets. I just adapted that to be able to just output arbitrary, like highlighted strings. So that makes it easier to look at when we're trying to make sense of this IR. But yeah, this function here, foo, has a loop. A starts at 0. When A is equal to 10, we're done. And otherwise we just increment A. And so here we have, you'll notice we actually have separate blocks, which we didn't have before a week ago. When we started this a week ago, we had nothing when we started, but so now we have separate blocks. And then, so let's see, we grab a literal value 0. We now have type information attached to each of these as well. And then we need to do, SSA does weird stuff with branching in order to get values, since you can only have a value that's assigned, like each value can only be assigned once, but you need to be able to like get the value from 2 different branches in the merged branch. And so there are some tricks for doing that. We use such a trick, but basically we use a phi epsilon style for those that know. Then we jump to our loop, and so basically we just set up our variable. We initialize it with this v0. That's our 0. This is our a. Real numbers. Hey, Matt, how's it going, man? And then we get into our loop. And so once we're in our loop, then we have our phi, which is just branch get. We have branch set, branch get. And so now we have our like current value of a, and we want to see if equal to 10. So we grab 10, we deref equals, we call equals with the right values. We get adds. Fucking adds. I saw somebody say that it's actually possible to turn all of the ads off. And I thought that wasn't possible. But if it is, then I'm going to do that. Because I'm not here to monetize. I'm here to show you. I'm here to expound. So yeah, we grab 10, we grab equals, we deref it, and then we call equals with our value, which is S1, and 10, which is V8. We check if that's truthy. We have we take a look at the operations here. If you look at op, right? So we have branch, we have truthy, we have dynamic call, we have var deref, we have literal, branch get, branch set, and jump and ret are all the ones that we're seeing here. I think we only had literal and ret when we started this on Wednesday. And so yeah, if the value that we get back from equals between our shadow 1 and 10 is truthy, then we will jump to if5, wherein we just grab this literal done keyword and we return it. Otherwise, we grab inc, we do a dynamic call on that. We do our upsilon, which is our branch set, to update the shadow variable, and then we jump back to the beginning of the loop. And so this is our IR is coming together. Our IR, I still struggle to say our IR, but it's coming together. And so let's see. Before we jump into coding, a couple other things. I had a call with the Clang dev who I work with. He's the guy who made the whole C++ JIT compiler in Clang. Well, it was outside of Clang before, it was called Cling, and then it was merged upstream into Clang. He's the guy who made that. And I was chatting with him about a separate project that they wanted some input on because they're building kind of a similar thing to jank, except for Python, where it's not a dialect of Python, but it's a Python library that provides C++ interop and JIT compile C++ and everything like that. And jank is kind of further ahead than all of that. So they wanted some input on that. But I also had this question for him about the Clang AST and whether or not we should, out of our IR, if we should be generating Clang AST, or if that is going to end up being more trouble than it's worth. And if someone's going to know, then he's going to know. And so that's why I wanted to make sure that I ask him before I start doing any code for this. And his answer was that we should not do that. He said we should not do that. And his reasoning was that, so as we discussed last week, and as I know, Clang's C++ API is not a public API. So it breaks even with minor version changes, from 22.0 to 22.1, there might be a breaking change in the C++ API, and that's just because it's not a public API. They have no promise for stability, and so on. And so I knew this, but was still wondering, maybe we can lean into this. Maybe we can establish some relationships to make sure that that the stuff that we're using doesn't get broken and blah, blah, blah. But he was saying that not only is this not a public API, and so we have to deal with all the breakages stuff, the stuff that we knew about, but also The problem is that Kling's AST is not designed to just be used for arbitrary synthesized AST creation. And the downside of that means that it would be very easy to synthesize an AST which is not valid or not standard C++. And the only way that we could know that is to have the C++ reference on hand in order to verify that. But that's not really going to be practical for us. I was distracted because I just realized that the instructions here, they don't actually have a closing curly for the block. We're missing our closing curly for the block. And none of this matters because this closure representation is actually just like a serialization format. It's not actually being read. It's just being printed. But I saw that and then I lost my train of thought because it bothered me. But it would be very not possible or probable. It would be very likely that we would end up creating some sort of AST that seems valid, but then when we give it to the optimizer, there's some undefined behavior, and then it ends up optimizing in a way that we can't predict, because optimizers can do whatever they want with undefined behavior. That's the whole point of undefined behavior, and that there's no real way of validating the AST in that way to ensure that we are always using it correctly and synthesizing correctly. And so that it would be possible, but that it would be a real uphill pain in the ass. And so that combined with the breakages, which we already knew about, makes it seem like, unfortunately, something that, a path that we probably should not take. Hey, Twishty, hope you're doing great. We started a little early today. I was actually ready at 1. I was like, let's do it. Let's do it. But then I was like, okay, maybe I'm not ready. Get some water and then prepare things and then maybe get out of my pajamas. And the next thing you know, it's like, oh shoot, it's actually almost 2. Devastating news, says Matt. Yeah, it's okay. I wasn't certain that we were going to be able to do this anyway. I knew I wanted to chat with him and get sort of like his blessing before we went down that path of trying to synthesize Klang ASTs. And so that means that we're already prepared with a backup plan. And so the backup plan is just C++ generation. And I discussed this with him and he was saying, oh, maybe you could generate C instead. C is a lot faster to compile. And in some ways we can. But the thing is that because jank is, we're seeing jank as a C++ dialect, we allow arbitrary C++, and we allow defining C++ functions within jank, and that's going to grow to like defining templates and structs and classes and like all of these things you're going to be able to do from inside of jank. And so you can't really compile all that to C because it is C++. And what he was suggesting is like, oh, well, the C++ bits you compile to C++, but then the rest of it, the glue that kind of brings everything together, you compile with C. And then you just expose the C++ stuff as C functions. Now, the problem with that is it works. It will definitely work. The problem with it is runtime performance. So in order to have all this stuff work with C, we need to use like pointers to void. We need to have type erasure. We need to have indirection. We need to have, we need to hide all this C++ stuff and put it into C terms. And that can work, and it would be faster to compile, but it would run slower. And the whole reason, my main goal with all of this work is to optimize the runtime of jank. Now, if we can optimize the compile time, great. And that was the main goal of generating Clang AST as opposed to generating C++. The goal there was to optimize the compile times, because the runtime performance between generating C++ versus generating Clang AST would be effectively the same. We're going to arrive at Clang AST by generating C++ anyway. We just have to have C++ generation and parsing in between. But then we still arrive at Clang AST. So yeah, we don't want to generate C because that's going to add indirection. That's going to slow things down. So we do want to generate C++. And then the last thing that I discussed with him was that he suggested that we could potentially look into LLVM MLIR. And MLIR is basically a higher level IR for LLVM that is designed to be extensible. And so you're able to create like dialects of it and then represent like higher level semantics in there, and then provide a mechanism to lower that MLIR down to normal LLVM IR. But I've looked into MLIR and it was just really complex. And like I didn't quite get it. And this Clang dev was telling me, he's like, yeah, I've been to like a few talks about it and I still don't quite get it. And I'm like, dude, you got like a PhD in this shit. If you don't get it, I'm not going to either. And I was like, with my IR, I can at least keep it simple, and I can get it, and I can work on the smaller bits. And he's like, well, actually, I'll tell you a bit about what he said with my IR afterward. But yeah, Matt, interesting that it would be possible to produce invalid Clang AST, assuming that you're already generating valid C++ code. But I guess it makes sense if the API is unstable. Well, the thing is that, yeah, C++ code is a lot easier to generate than the AST, because C++ is very complex to write, but it's even more complex to compile. And you're basically skipping over all of the convenience that you get when writing it, and you're needing to jump right into it when you're generating the AST. And that means that jank, the compiler, would need to know a lot more about C++, things like C++ value categories, for example, and initialization rules, and like implicit conversion rules, and all of these sorts of things in order to generate the correct AST. So yeah, in my experience, like having worked with Clang's AST, which we do for like the interop stuff that we have in jank, it's very complex. So like I can already see how this would end up being a problem. And I knew that this would, like, working with the AST was going to be really, really tough, because already I've had to work with Clang AST in order to do things like operator, or not like overload resolution, for example. Overload resolution is so involved because you need to factor in, oh my God, the fucking rules for this. You need to factor in, like, okay, so you want to call foo with A and B. It's like, okay, so foo, you're doing like std : foo, right? But you don't just go into the standard namespace and find all of the foo functions. If only it were that simple. C++ also has this thing called argument dependent lookup, ADL, which allows you to change the namespace that something resolves to. Like you change the namespace that foo resolves to, depending on the arguments that are provided. You need to consider those namespaces, the namespaces that the arguments come from as well, and you need to factor those in. And like, so there's ADL, and then there's like member lookup, and you have like friend functions, and then you have like operators and their overloads, and it's so much. And I had to hack all this together, actually with the help of some AI, with Klang's AST and C++ API, in order to get overload resolution working properly. And so I can see, and like it wasn't straightforward at all. I couldn't just say, okay, go do overload resolution with these two arguments and the function foo. No, you need to piece together all of those things yourself, because there's no high-level API that allows you to convey that idea, because they haven't written the API to be used by third parties. And yeah, what a nightmare. I did some Java type checker stuff one time, and it gets shockingly non-trivial with the more sophisticated parts of the type system with overloads, etc. So I managed just like that, but worse. Oh yeah. Yeah, because C++ is so much more complicated than Java when it comes to these things. Well, Java has the whole JIT optimization, JIT compilation, everything like that, which C++ does not have. But when it comes to the type system and templates and overloads and argument dependent lookup and everything like that, yeah, C++ is nastier. Yeah, so I totally get it when he says, don't do this, because it's just gonna be too much. Now, speaking of too much, the other thing that this Clang dev told me when I said I was making my own IR is he said, oh, that is something that only companies do, where they have like, multiple people working on it full time. You might not want to make your own IR. And to that, I said, well, to that I showed my screen, and and then I showed some jank code, and then I showed the IR generation that I have already. And I was like, look, I already have like basically all of Clojure semantics done except for try and case and let fun. I haven't done IR generation for them. And I said, I already have IR generation for all of this now. What am I missing? Like, are there big pieces that I am missing? And he said, well, it's more of an 80-20 thing. He's like, you could probably get like 80% of the way in terms of like optimization passes and everything like that. But if you want to get the other 20%, then it's just going to be an insane amount of work. And that's probably accurate, but I'm okay with that, because right now we're at 0% in terms of what jank is doing for optimization, and getting to 80% is a really big jump from 0% to 80%. So yeah, I'm not expecting that jank, like the IR optimization pipeline that we're going to have, is going to be like world-class state-of-the-art, but there are a lot of Clojure level semantic optimizations that we can do that the C++ compiler and LLVM IR optimizer just won't do. They won't have the ability to do that. So for example, function calls in Clojure operate at the var level, right? So when we call equals, we have to grab Clojure core equals. We have to do a var deref, And then we have to do what jank calls a dynamic call on that. And dynamic call has to take some function object and then figure out like, okay, not only is this thing callable, but also what arities does it support? Because here we need to dynamically dispatch to the correct arity. And this gets harder. It's not just, okay, we have arity 1, we have arity 2, we pass 2 arguments, there we go into arity 2. If the function is variadic, or at least one of the arities is variadic, then we then need to figure out, do we need to do packing or partial packing? For example, if you have an arity that takes, so let's say we have a function here, function that takes A and B and then everything else, right? And so let's actually just say let's say I do one of these. And then if I call this with 1, 2, 3, then I need to actually say, okay, so 1 and 2 are fixed arguments, but 3 needs to be wrapped in a sequence. So that way it can then be passed as the third argument, which is a sequence of args. And so this actually ends up being called with something like this. And so we have this whole, wait, where is that? Fuck, where is all that? We used to have it in, I moved things around and now I don't remember dynamic call. Where are you? Is the LSP going to help me out here or what? There we go. Oh, it's just in call.cpp. Oh yeah, cool. So yeah, for dynamic call, we have a bunch of these fucking overloads, right? So here we just take the source function, no arguments. We still need to check like, do we provide, like, cause it could be one of these functions. And so if you call it with no arguments, like so, we actually need to create an empty sequence and then pass that in. So we actually need to pass an argument, but here's one argument. And so we have like, okay, we need to grab its arity. And so jank actually uses like a bit mask in order to detect the arities. And there's a case for ambiguous arities as well. And so we need to like, for each of them, and this ends up being a lot of code, all the way up to the max like fixed arity that we support, we need to detect how to actually unpack all of these, or rather how to pack them to make the call. And so this is all like closure level semantics. And by the time we get into C++ like that we generate, or LLVM IR that we generate, LLVM has no way of optimizing these things. The only way that we can optimize this is if we do so at a closure semantic level, and we understand things like, we're doing a dynamic call on this var deref of this thing, right? And so then we can say, okay, so if we know the type of this function object, we don't need to do a dynamic call, because now we can know whether or not that function is variadic, and then we can skip the dynamic call, and that means that we get to skip all of this code, right? There's a lot of code going on here that includes like making whole fucking sequences. We get to skip all of that. Anyway, so I was trying to explain why we would want to be able to do this in our IR, and how there's no way that this is going to be done for us. And so although I realize I'm taking his advice for not using the Clang AST, for not synthesizing Clang AST for our code gen, I'm not actually taking his advice when it comes to making our own IR, because to me, it's what we need to do. Like, I'm not going to be able to do the optimizations I want to do unless I have an IR that operates at the level that Clojure operates on. So yeah, that's a lot of work, but I also, as I said last week, like, I'm prepared to spend the next 6 months on this, solo, just focused only on this, if I have to. But we'll see. I made a lot of progress just this past week to get basically all the Clojure, like all of the Clojure semantics encoded in this IR, which I'm pretty pleased with. But we still have, to do code gen from this IR, and we still have to do all of the optimization passes that we're actually going to end up doing here. Anyway, so that was how that call went. This is our new direction. We unfortunately are not going to try to do the Clang AST stuff. And we're just going to stick with our own IR. I think he brought up an interesting point, which is if we stick with our own IR and then we write our own optimization passes, everything like that, it's possible that we could explore using an LLM to port from our IR to MLIR and just sort of see what would be like if we generate that instead. I think that would be an interesting thing for somebody else to try once we get to the point where Jank's IR is like stable and we have useful optimization passes on it and code gen from it, everything like that. But it's not something I'm going to worry about right now. Matt, you think making an IR is the right choice, even for your own sanity? It's nice to have, and even if you don't do a ton with it in the end. Yeah, I think so. I think that for things like interpreting as well, or for targeting other backends, like if we want to do code gen to WebAssembly, like I know LLVM has its own way of doing that. But if we want to have our own sort of code gen to lower to WebAssembly, like we could use the built-in like WebAssembly GC for that as well. Hey, I borrow checker, by the way. Welcome. I hope you're doing great. Also, thanks. We just hit our 220 follower goal. Woo, that's what that noise was. So I think that having the IR is going to be nice when it comes to like lowering to different backends as well. And that way they'll still be able to benefit from all of the optimizations that we're doing. Yeah. So I agree with you, Matt. But it was a little daunting to hear this Clang dev tell me how concerned he was with the size of like what we were taking on. Thanks for the raid. I borrowed check, by the way. Welcome, Zaflins. I hope you had a great stream. I borrowed check. Yeah, go for it. Sleep well, get some rest. Zaflins, we're working on the jank programming language, which is a native dialect of Clojure that is also a dialect of C++. And so it allows you to do all the sorts of Clojure, Lispy, functional programming shit, but also at the same time allows you to just reach in arbitrarily to C++ and has a just-in-time C++ compiler alongside it. And so you can do all of your interactive like REPLing and everything like that in C++ land as well. Baller name already invested. All right. Okay. So that's an interesting shape for a cup you have there. Oh, this is a mason jar. You guys don't use mason jars? Mason jars are fucking great. The thing I like about this is it's like 1,000 milliliters. It's like it's big. It's a lot of water, but it also has like, rings so you can put a lid on it. And so if you're making protein shakes or whatever, then you get to use the same cup. You just, put a lid, put your stuff in there, shake it around. It's great. C REPL sounds fire. Yeah. So we already have like a whole nREPL server. nREPL is this protocol that we use in Clojure land that allows us to connect the text editor to the running program and send new code to your program and build it up as you go. We already have that working in jank, and so you can be like arbitrarily including C++ libraries while your game is running. Include a new C++ library and start using it without restarting your game. I use games because that's just how my mind works and where my background comes from. But it could be any C++ application, any Clojure application. I gotta add this closing thing here. That's driving me nuts. Do I make games with jank? Right now, Kuviman. Where do I recognize that name from? Kuvi. I swear I was just watching your stream. Yeah, I was just watching your stream. Hope you're doing great. And I don't make jank games right now. Cass, yeah, Cass, exactly. Yeah. I watch your stream all the time. So I don't make games in jank right now because jank isn't stable enough. Jank isn't production ready, and so right now I'm only making jank. Too busy yak shape. Hey, too busy. Look, if you have a hairy yak, then shaving becomes important, right? At some point, your yak gets hairy enough to where shaving is the highest priority thing. There we go. Now we have this something drawing the rest of the owl. Yeah, Kuiman's the goat. No, I refuse to accept that, man. I'm not yak shaving. I'm writing a fucking middle end for my compiler so I can optimize it so jank can be the fastest Clojure around, even though it doesn't have a JIT optimizer. But we'll see. So anyway, back to what I was saying. No, I'm not building games in jank yet, although I will. You just wait. I will. The nice thing about jank, and I'll say this as I'm spinning all this up so we can actually get to some coding, is since you can, it is C++ and it's also Clojure. It means that you get to, like, if you wanted to build a game engine, you can write it all in jank, and the high performance side of things, like the game engine, can be more C++y, can be statically typed, and you can use parametric polymorphism and take advantage of RAII and all of that good stuff. And then any parts that are not performance critical can be more Clojure-y. And so they'll take advantage of persistent immutable data structures. They'll be, your objects will be garbage collected, and you won't need to worry about, lifetimes or anything like that. And those two sides will just seamlessly work together. You can call functions from one side to the other side. You don't need to define bridges or like declare things. You don't need to generate bindings. They're just They all work together. They're all one code base seamlessly. Okay, so what we were doing is we were filling in more of the IR generation. And so there are still some generation functions here that I haven't handled. This is like forward declaring every AST node that we have. And so they're like all the C++ side, which is actually, so this is 14. We have a total of 35. Yeah, so a little less than half is C++, 21. And I've done most of these. Like I already have IR generation for most of these. And so we just need to fill in the rest. And I think that what we can do is we'll do these list vector map and set now, because those are going to be pretty easy. The nice thing about these, so I want these to be their own I level. I want them to, I don't know where I level came from. I want them to be their own IR operations. So I want like a specific instruction for creating lists and vectors and maps and sets, I think. The nice thing about that is one of the things that we're going to be able to do is in compilers, this is called escape analysis. Zaflins, we don't have a Discord, but we do have a Slack, which is just where all the Clojure people are. But if you go to like Jenklang, then you'll see that there's a link to our Slack and GitHub and everything like that, all on jenklang.org, as well as the Jank book, which is if you want to like learn more about the details, then the Jank book is where to go. Maybe we should be on Discord, but like the Clojure community as a whole is on this one Slack. And I'm kind of like, I didn't want to pull people away from that. I want Clojure to succeed because Jank is Clojure. And so I would like to have everyone together. I brought up this browser because I was going to talk about escape analysis. And so there's this, I don't actually know if I've never read this article. I don't know if it's going to be helpful, but no, there's too much here. So I'll just explain, like, if we're going to make, if we do something like this, and maybe we take a parameter, and we turn this into a map, and then we just do something like some sort of operation on this map that doesn't actually capture the map. Like, let's say we just do like a get MA. Of course, we could call the keyword here, but it doesn't matter. This is, of course, a very simple example, but there are more complex examples that would also apply that I could show you as well. Here we create this is actually creating an array map, but we create a map, and by default this would be GC allocated, and so we have a heap allocation here to create this map. And then all we do is we just pass this map into get, and we get a value from it, and then we don't do anything else with the map. And so escape analysis basically allows us to track which functions are, think about it like this, that you want to track which functions are going to capture their inputs, where capture means like hanging on to in some way. Maybe it hangs on to it because it goes into a closure. Maybe it hangs on to it because it it puts it into an atom, or maybe it hangs onto it because it adds it to some other data structure or something like that. But if you're just doing like a print, or here if you're just doing a get, or if you're just doing some other sort of like read-only operation on this data structure, it doesn't actually need to, it doesn't actually capture it. And so what this allows us to do, so borrow checker, yeah, kinda. But in general, this term is called escape analysis. We're not checking for validity. Like that's the difference. Is borrow checker is generally going to tell you if you're borrowing something like further than you're allowed to. We're just focusing on optimizations here. And so escape analysis allows you to know that get is not going to capture M in any way. And so if the only usage of M is for, this function that doesn't capture it, we don't actually need to dynamically allocate this map. Right? So we still need a map, sure, but we can stack allocate it. Right? So when we're talking about the generated C++ for this, instead of doing something like so we'll have some function that returns an object ref, and it's called foo, and it takes some object ref A, and it takes some object ref B, and we'll get inside of this, and also I think I can just drag that. And so we'll say like, okay, auto M, and normally we would do something like, we would say make box, and then we would create a persistent array map, and then we would give it like A and B, and then we would do the key A and key B. That's a shorthand syntax because I don't want to deal with interning things right now. But we would dynamically allocate M here, and then we would call get, and we would give it again this, and we'll do a return here. So this is basically like this sort of C++ that we would generate for this. And as we can see here, like there's no need to dynamically allocate M. And so what we could do instead is we could just say, okay, so we want a persistent array map, got it. Let's just do this. And then here where we want M, we're just going to give it the address of M. Hey, Johnny, just found out you're streaming on Twitch. Cool. Yeah, I saw I saw the follow come in actually right before I started streaming. I appreciate you. Thanks for jumping in. Glad you're interested and happy to find us. So escape analysis, the way that we're going to do it is we're going to keep track of which functions, we're going to keep track of which functions are pure versus which functions do effects, but we're also going to keep track of which functions capture which of their parameters. And then if we know that some data is never actually captured, we don't need to dynamically allocate it. We can just stack allocate it. So the difference between these two functions is huge. It's huge. Like, sure, this is at least one dynamic allocation. It's probably multiple, because there are this is a whole data structure that has internal bullshit going on, but it's at least one dynamic allocation. And this is at least one fewer. But when we're talking about dynamic allocations in a loop, so if we take, for example, something like fib, where here we have a function that only calls itself, right? It's not calling anything else. So we get some n, we check, if we're done. If so, we return n. Otherwise, we only call ourself. Now, in this case, when we do something like call minus on n, right? escape analysis can tell us here that Fibonacci doesn't capture n. It's not being stored anywhere. And so here we can call, like we still need an object because this is a parameter, and everything at the, like everything that's a parameter in our default closure world has to be like a boxed object. But it doesn't need to be garbage collected. It just needs to be an object. And so it could be a stack allocated object that we grab the address of. And so here we can do this subtraction. Normally in Clojure, this subtraction gives you an allocation, right? You're going to need to allocate the number that is the result of this. This will be its own allocation as well. And then this plus here will also be an allocation. So that's 3 allocations right there per call. Now with the escape analysis, this is not a dynamic allocation. This is not a dynamic allocation, and plus will be because it's in tail position and we need to return it. And so we can't have that be a stack allocated object because we need to actually return that object. So we can't just return the address of the stack allocated thing. So this would, like escape analysis would allow us to turn 3 allocations per call into 1 for Fibonacci, which is huge because that's something that you're going to be calling over and over and over and over again, right? And you get a third of the dynamic allocations. This is not something, as far as I know, it's not something that Clojure JVM does in terms of optimization, because Clojure JVM just relies on the JVM being superb, but we can't because we don't have the JVM. You know, we don't have a hotspot optimizer. We don't have all of these things. We need to do the extra work ourselves so that we can match that performance. And that's one of the things that we're going to be doing with this IR. I saw that there were some messages. So, Johnny, you're making a very tiny subset of Clojure as your bachelor's thesis with C++ and LLVM. Super cool. Nice. There's not a lot going on in this space in terms of prior art, so that's cool. I hope that that is enlightening. Feel free to share it if you have some code you want to share. Drop a link. Okay, so we are doing. I was telling you about escape analysis, and the reason why I was going into that is that, yeah, so the creation of these lists and vectors and maps and sets, I want to be able to know also like whether or not these values are going to be escaping, and then we can just optimize the creation of these to be stack allocated instead. So I've moved a lot of this stuff around in the past week because we were just doing everything in one file before, but now we're not. Tiny Clojure. Nice. I'll take a look. I'll take a look later. Right now, trying to get this done. Okay, so we can add a new instruction. I think we'll just add a new one for each of these. I just want to check. So literal is a noun. Varref is a noun. Named recursion is a noun. Jump is a verb. So we're not actually super consistent that like every instruction is a verb or anything. So I don't really have a problem just calling this like list. Yeah, I think I'll probably just call this list. So where do we want this to go? Probably after literal. So the difference you may be wondering is like, oh, why do we have a literal instruction, but then we also have list and vector and map and set? And the reason for that is that you can have, so if you have a map literal, right? like this, okay, this is a literal, and this would show up, this would use the literal instruction. And the reason it's a literal is that it's a map that's written out literally, and every key and every value is also a literal. But if you have something like this, where this map depends on A, which is a parameter, then this map is no longer a literal. And so this would instead be a map AST node, which is this is the like map expression. And so for that, we need to evaluate, all of the shit involved separately, and then we can create the map. So that's the difference between the literal as well as the non-literal version. Okay, so for list, we don't need to take the type because we're gonna know the type. The type of that is going to be a persistent list. We do want the name, and then do we take value? I think we're gonna want for this probably a native vector of identifiers, and we'll take that by our value. We'll call that values. And so this will go here, and we'll bring that like so. That should be good. And it's gonna be a chore to like do all of these separately. So I'm just gonna do them all now. And I'm gonna call this persistent list, I think. That's annoying. Persistent list. And this I'm going to call persistent vector. And the main reason why I'm calling a persistent vector persistent list, aside from that's what those data structures are actually called, the main reason is when we get to set, I don't want an instruction that's called set on its own, because that could be misconstrued to be like a mutation oriented thing. We don't have anything like that. So just considering that. As you said, JVM closure implementation is interesting. There are basically no implicit optimizations, and they have a ton of inefficient legacy code in the compiler that haven't been touched in a long, long time. But hey, if it works, don't touch it. Yeah, I mean, closure JVM just depends on the JVM to do all of their optimization, basically, and they get away with it because the JVM is that good. Persistent map. So this is not going to be array map or hash map because we're going to choose the correct one based on how big the values are. So we'll just call this persistent map. J. Radcliffe, where's this come from? How did you make this connection, Zaflins? Explain it to me. Okay, so for the map, we need probably pairs. I think if we take a look at so we have a vector of pairs here for the expressions. So I look a bit like Daniel Radcliffe. I have not heard that one before. But I'll take it. Daniel Radcliffe is a handsome man, if I say so myself, and I do. Okay, so that's map, and then persistent set is the other one. This one we should. So there are actually three types of maps in Clojure. There's a persistent hash map, there's a persistent array map, and then there's a persistent sorted map. And so a map literal will either end up being an array map or a hash map. It'll never be a sorted map. And similarly, a set literal will only ever be a hash set, even though there's also a sorted set. There is no array set in Clojure, but there could be. So I wonder if I want to say persistent set here or if I want to say hash set. I don't like that I wouldn't say hash map here, but this is mainly just the difference between how Clojure does things. Instead, I'm just going to leave a comment. So this is always a hash set, I think. So and for this one, we can actually just get rid of this pair thing here. We don't need that. Okay. So that gives us list and vector and map and set, and that defines our instructions. Well, it declares our instructions. So now we need to actually define them. And so if we jump into, I'll just grab this guy and then I'll jump into the constructor for this, and then we're just going to build from here. So I will grab this, and so we're going to do values, and we'll do a move of values, and now we just need to get the type. Now we need to get the type. So this is a Clang representation of a C++ type. And we don't have an easy way to get access to a persistent list ref type. From here, we're gonna need to make a helper for this. But I have some. Ooh, I do have a literal type helper, which I could use. No, I don't like it, because then I'll need to dynamically allocate something just to get the type. I don't like it. So yeah, we'll do here persistent list type, persistent list ref type, and then this will be a vector, and then vector will be map, and then map will be set. I have no idea how that happened. Set. And then we'll jump into the definition of these, and we'll do that. And then we're just going to do the same shit here. So this is var persistent list. Yeah. So this is basically going to use Clang to resolve the jank namespace, then the runtime namespace, and the object namespace, and then it's going to find this. And so this is actually a like persistent list ref here is actually a C++ alias. And so I'll show you, like in vector, we have right here persistent vector ref. So what we're doing in this bit of C++ string right here is we're just in time resolving this jank runtime object persistent vector ref to be the type that it represents. And so that's a bit of like just-in-time C++. We're not actually doing just-in-time C++ compilation, but we are doing sort of just-in-time C++ introspection. And so there's, we need a hash map on this. Is it a hash map or is it an array map? We need to clarify. And how do we know the type of our persistent Yeah, so in order to have the type here, we're actually going to need to know if it's an array map or a hash map, which means we're going to need an instruction for both. Kubiman, what's an array map? I'll tell you after the ad. Okay, so map, array map, array map. So now that ads are back, ads are done. This is a set. An array map, Kuviman, is also known as a short map. It's a map that is not stored internally as a tree or any sort of like table or anything like that. An array map is actually just stored as an array, given, hence its namesake, and the keys and values are interleaved in the array. So lookup in an array map is lookup by key in an array map is order n, but due to the data locality of having all of that whole array in memory, it's actually faster to do a lookup in an array map order n than it is to do a lookup in a hash map, that's actually amortized constant time, because there's just lower overhead, right? So a hash map is a better big O complexity, but it has a higher overhead. Array map has a very low overhead, but worse complexity. And so Clojure uses array maps for small maps. If it's eight keys or fewer, and you have like a literal in some Clojure code. So if you do something like right here, A and B, this will not be a hash map. This will be an array map. And then if you do an assoc on that to like add more keys, more values, it'll be an array map until you add the 9th key, and then it'll promote your array map to a hash map. Yep. So it's purely an implementation detail of Clojure to optimize for small maps. And this is mainly because in Clojure, we don't define, for the most part, we don't define our own data structures, right? If you have a person that's some sort of entity that flows through your system, you don't define a struct or whatever that makes a person. Instead, you just use a map, and semantically, that map represents a person. And so if a person only has a name and an age and an address, that's just 3 keys. That's just going to be an array map. Okay, so list vector array map, hash set is what we actually end up with. I need to jump back into here and right. And then I was writing out the types. So we need array map, and we need hash map, and then hash set is what we're going to do. So this is hash, and then hash, we get array, and then hash, we get array, and then here is hash. Yeah. And so this ends up being a set, set. Okay. Now, here I can just do persistent list ref type, that exact guy right there. Perfect. Now we'll do list becomes vector. And then here, vector, and actually the rest of that just stays the same. So we can then jump into array map and vector array map. And then this was a pair of identifier to identifier, and then values, and then vector, it becomes array map, and then move values. That's all the same. And then finally, actually semi-finally, hash map. And now finally, we have hash map hash set. This is the sort of thing when Rich Hickey says like why he doesn't like types, right? This is what he's talking about. And this is like, okay, I just added, you know, however many types, like 1, 2, 3, 4, 5. I just added 5 types, right? And I'm spending all of this time writing fucking constructors, you know, to make sure that I can construct these types with the right value and that there's, you know, storing all this shit. And like, when you just work with maps, and vectors and lists and keywords and strings, you don't need to do any of this. You don't need to do all of the pipe work to make sure that, you know, each of these types is fully implemented. Like, okay, if an array map stores a vector of pairs, great. In Clojure, this would just be a map, and then inside you would have a key that is called values, and inside of that would just be a vector of vectors, you know, or maybe a vector of map called key, and a vector of map that has key and value, you know, for these things. But in C++, of course, like we have to define all these things as to please the type system, and it ends up being so much code. So much code. Now we've written the constructors for those, but we still need to write the print functions for those. We're not even done. And so yeah, it's when I'm doing all of this that I think about why Rich Hickey shits on types. And that's not to say that he's necessarily right, but that's not necessarily to say that he's right generally, but when you look at specific instances of, oh, okay, C++ or Java or whatever, then it's like, yeah, the types there are really like, there's so much ceremony involved in getting all of that, going, that you spend so much of your time. If you create a foo, then all of a sudden you need to create a foo constructor and foo destructor and, you know, copy operators and blah, blah, blah. And then you got to overload all these things to take foo. I still can't spell persistent list. Yes. And then values will be values. And then this is going to need to be a vector. And so we're going to need to take all this stuff. Actually, let me take this and then bring that down here, and then I will just delete up to that, and then we'll close that, and then we'll do our type like so. And so yeah, we're still just like string building for our serialization here. But it is pretty easy. And I'm just going to take one of these. So this is like probably just temporary. I've not decided yet. We'll probably end up converting this to where we can just take these instructions and turn them into actual Clojure data, as opposed to turn them into a string representation of Clojure data. But I don't actually know if I'm going to need that yet. So we're gonna find out. So args values, and then I'm gonna call this guy value, and that's gonna be called value. Okay, that's that. A lot of these are gonna look pretty similar. Hey, LSX BCG. I don't know how to pronounce that. Welcome. Hope you're doing great. Okay, so that's persistent list. Yeah, this ends up being a lot of code. But in terms of how it generalizes, I don't think it's worth generalizing to save the code. It's easy enough code. This is basically the mentality of Go developers. Like, oh, I have so much code, but it's all so simple that, you know, I don't actually need to refactor it. I try to go to the matching for that, and it does not match. So we'll have to do this more manually. So that was vector, and then we want array map. Doing all right. Just heard back from 2 companies. Sort of moving applicant. Try to cheer up by watching other coders. Sorry to hear that. Also, what is that about right there? That should go away. That should go away. Yeah, trying to get a job is it's fucking tough. I've been there. I'm so sorry to all of you with headphones on. You ever take a breath and then get like spit in your lungs? Oh. Oh, I'm alive. Oh. Value first and second. Why am I doing this character by character? We're just gonna do this and no comma and then this like so. And then value first and value second. There we go. And that's it for array maps. And now we can do this for hash maps, which is going to be the same shit, except array turns to hash, and then that's that. And then finally, for sets. Hash set, vector, hash set. And, oh, also, this just goes here. Man, I don't know how I didn't catch these before, but all of these are wrong. There we go. Oh. Okay. So yeah, we were getting linker. I didn't look because I knew already, but we were getting linker errors before because we didn't have the print functions. So we can see. Oh wait, this is a linker error for the constructor. Oh, okay. But anyway, so we compile and we link successfully now. And so we get rid of this and we don't need that open anymore. Now we can actually start to add this to our builder. And so our builder exists in a separate file now as well. Like I moved instructions and builders and printing out into each their own files, just because they all have kind of their own isolated code. And then this IR processor is just for walking the AST and generating the IR. So now we need to just add this to our API for our builder to be able to easily create these instructions. Yeah, finding a job sucks. I think I'm going to chill for a bit and then maybe go back to LeetCode tomorrow. LeetCode, man. Yeah. Yeah, in my experience, networking and open source work are like have been the most useful things when it comes to finding a job. But when those don't pan out, then and you have to fall back to like elite code style interviews, it's tough. So persistent list, and then what are we gonna take for? I guess we just take the same native vector of identifiers here called values. Now you're good. The mood is not ruined. We show compassion to those who are struggling. And set. Okay, so list vector array map, and then hash map, and then hash set. And then the only difference here was that this was pair of identifier. So like all of this fucking glue code, you know, like all of this glue code wouldn't exist in Clojure as well. But it's like, oh, added new types. Gotta overload. But we're getting there. We're getting, this is why chat, we're building a language that has the power of C++, but doesn't have all this bullshit. Because I know. I don't actually know how much I want of this, but I'm just gonna take it all right now. And then I don't need the type because we don't need to specify that. I don't want to delete all that. I want to delete some of that and move, and then persistent list. And then if we are in tail position, we do need to generate a return, but I need a type. And so I'm going to need to grab the type by, because I don't want to duplicate it here. I'm just going to do type. It's going to do that. Okay, that's fine. So now we should just be able to paste this here and then change this type into vector. And then paste this here and change this type into hash set. And then, oh, actually, because values is just called the same, we don't actually need to change these either. So this is array map, and then this is hash map. And I think that all of these, I think that that'll just compile. It does. So now we can finally do this. So now we can do B persistent list. We can give our expr position because we need to know if we're in tail position or not. And then we need our values. And so our values is gonna go here. And we're gonna do a JTL move, sudo STT move. So we're gonna make our vector of identifier. We're gonna call that our values. And then we're just going to loop through. So we're gonna have our expr. We're gonna loop through our value expr. Figure out what I want to call these values. And so we have a bunch of expressions here, and we're going to need to do a values in place back on, we're going to do the gen of value expr, and we're going to give it the builder, and we're going to unwrap that because that's going to give us an optional. we could also, we could do a reserve of expr values size, which is just good practice. No member values. What the fuck? Don't suggest values to me then. What are they? Oh, they're called data expers? Lame. Gusto smell. Sorry for off topic. First time PC owner. Anything critical to know about debloating automatic driver updates, telemetry for Windows 11? The best place to get advice would be from a code wizard. I can't help you, Gusto. Lo siento. I don't use Windows. I haven't used Windows in 15 years. Last time I used Windows was 7. Have you tried Linux? It's or Mac OS? Persistent vector. And so we just need to add expr. All good. I appreciate the follow. And I hope you have a great day. And I hope that you get the answers that you're looking for. I have seen Gusto. I've seen that there was like a GitHub thing for like Windows deep load. My wife uses Windows, and is this what I was? Well, this has 43,000 stars. So if you want to measure things that way, then that was interesting. Yeah, maybe this is the thing I had seen that other people were looking at. But the thing is, like with Windows, running third-party software is always terrifying because you have no idea what's malware and what's not. So I can't actually recommend this. But there are some things like this that allow you to disable like the AI bullshit and everything. I can't vouch for it because I've never used it and I don't trust any of it. Windows software like administration is terrifying. I have no idea how people manage that. I think in general they do it by not thinking about it. They're just like, yep, this is fine. This is fine. Okay, so this should be hash set. Hash set. I appreciate the follow, LSX, as well. Okay, so the only other thing here that changes is for maps. We need to, here's the thing. We need to conditionally make a hash map or an array map. So first off, this is going to be a vector of pairs. So this is a pair identifier, like so. And so data expers, is that actually, I guess they're all called data expers, which is nice. I don't know why they're just not called value expers though. I would probably prefer that. It's definitely not fine. Yeah. Yup. So, okay. So there are a couple things. So first off, we need to grab all of this and then we need to do this for first. We need to do this for second, like so. And then here's the final thing. We need to say, and I probably have a array map. There we go. So if the size is less than or equal to the array map max size, then we get an array map. And then otherwise we get a hash map. And so this guy, this comes in through this include, and Kling's actually going to give me this include, but it's going to do it in the most annoying way. First off, it's going to use quotes. And secondly, it's going to put it at the very top. And I don't want any of that. I'll put it here, and I'll change the quotes to be angle brackets. And that's fine. Cool, save that. So now we have IR generation for lists and vectors and maps and sets. And so we should just be able to use these in any position, tail position, or otherwise, and have them work in our IR. And I'm sure that that seemed super easy. Let's see. So let's say we want to do something like this. Can we represent that? Do we fail? Okay. So the first thing I look at is we get full output. We don't see any errors. And our block ends in a ret. So every in SSA, and well, combine that with CFG, like every block needs to end in a terminator, and they can only have that one terminator. So we didn't fail that, which is great. So we have the literal A, we have the parameter 0. So parameter is its own operation. This is everything, like sort of every operation is a value, and everything you want to do is an operation. So we can get the 0th parameter. Right now, I'm not actually naming anything. Like our parameter is actually called A, 0th, and then our first one is called B. I could call these A and B. I just haven't dealt with it because there are issues of like, well, what if, there's shadowing and something else is called A. Right now, I'm just generating unique names for everything else. And then I feel like I can clean this up later and go in and start adding in like useful names where possible. But to start with, it is actually simpler to just have everything be a unique name. And since I'm working on small cases anyway, it's relatively straightforward to follow. Jank has a functional test suite of like 700 or 800 different small Jank test files, and that covers like basically all of the functionality, including all the C++ interop that we have as well. We have other test suites like a unit testing suite for the lexer and the parser and for some other aspects. And we have an end-to-end testing suite as well for things like command line arguments and AOT compilation and whatnot. But the functional testing suite is what covers the bulk of the compiler right now. And that's just made up of a whole bunch of tiny files. I'll probably do that in a different one. Chess Jank. And so we just have all these, several hundred files that are broken up into directories that cover a bunch of different things. And this is what gives us sanity. And so we don't actually need to worry about, like when we're trying to make all these tests pass, we don't actually need to worry about helpful names there either, because each of these files is small enough to just focus on the one thing that it's actually, trying to test as well, which means that we can get away with having generated names for a long time. Like until this is kind of done, we can not worry about the names. Anyway, so we grab literal A, we grab the 0th parameter, we grab the literal B, we grab the first parameter, and then we do a persistent array map. Perfect. Values v0, v1, yep, and then v2, v3, yep, and Then we get literal A again. Now, see, this is the sort of thing that we can optimize, right? So we're getting the literal A twice. We could just get this once, and then like here, V5 doesn't need to exist. We can just reference V0. So we can either, I don't know if we're going to optimize this during our IR generation, or if we're just going to optimize this as a separate pass. It'll probably just be a separate pass, because you don't really need to complicate IR generation any further, because we're not only going to do this for literals, we're also going to do this for things like parameters if you have to get the parameter again, or if you create the same, array map twice in a row, like we can just use the same one. It's just a deduplication of all sorts of things. So we build the map, then we grab A, then we do a dynamic call on A. And so that's what we have here, where we're calling A and we're giving it the map, which is totally valid in Clojure, to pull that key out of the map. And we get the result of that, which is V6, and then we return it. Nice. I'm pleased. Pleased. So similarly, if we were to change this to hash set, that would also just, like, really the only change that we're going to see here is that we have a persistent hash set that just has 4 values, and the rest of the stuff is going to be the same. And similarly, if we were to change this to be a vector, then we would see persistent vector, and then all of our values, the rest is the same. And then finally, for completion's sake anyway, so we want to change that to be a list. Now this one, because it's not a, if you want to do a list literal, you have to quote it. We're not going to be able to get a list with A and B in it like this without actually calling Clojure core list. So here we're going to be creating the symbols A and B. And so because that ends up being a literal, we don't actually do persistent list. Wait, why do we have persistent list? How do we make a list that's not literal? We have an AST node for that. Wait, no, it's called expert list. Right here. So we use this for packing arguments, and that's it. Interesting. Interesting. So if we wanted to show that, what we would do is something like a print line, and then we would do a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So here we should end up packing, I think, 11 through 20. And there was our persistent list. And so, yeah, we do V10 through V19, and V10 is 11. So yeah, 11 through 20 gets packed into a list. And then we end up calling print line. We give it V0 through V9, which is 1 through 10. And then the rest we give it already packed inside of this list. And then depending on what print line wants, we're going to unpack some and pack some more. And this is why dynamic call is actually quite expensive. And it's one of the things that semantically we can optimize with our IR, especially if we are in some modes, like if we have direct linking enabled and we can know the type of print line, then we don't need to do the dynamic call, because we can see like the arity that we want to go to. We can actually pack things the way that we want to pack them, the way that we need to pack them in the most optimal way. Okay, but that's how persistent list is used anyway. So we know that works. Nice. So let me. We don't need this, and don't need that. And now we're back to here. Cool. So let's scroll through and let's see what's not done. Def is good. Var ref, call is good. Primitive literal, list, vector, map, set, local. Okay, so nested functions we have not done yet. And in order to represent nested functions, we're going to need to... Right now, we're only worrying about IR generation for functions. We're going to need an IR representation of like a module or like some set of functions, some higher level thing than just a function. I'm not ready to do that yet. Let's see what else we have. So recur is done, and that's recur in both a loop as well as function recur. Recursion reference, named recursion, let, and loop are both done. Let fun is not. Let fun. Yeah, let fun's going to be a pain in the ass. There's do, there's if. Throw is done, try, and case. Try and case. Case might be a fun one to do. Try might be a fun one to do as well. Yeah, let's do one of these. This is going to be a lot less boilerplate and a lot more like, a lot more IR in terms of generating more blocks and creating, like, merging things together, everything like that. Let's do this. We'll do try. But I'm going to fill up my water before we get going on try. And I hit the restroom as well. I will be right back in just a couple minutes. Hang tight. All right. We're back. We're back with more water. Let that be a reminder to all of you to hydrate. When people ask, how do you do it, Jay? How do you make all the stuff you make? The answer is hydration. Just drink more water. Okay, so for try, we're gonna need a few different things. So if we take a look at, let's do something like, we're gonna want like a try. We're gonna want a throw. We're gonna want a catch, and catch is gonna be jank runtime object ref, and then we're gonna want a print. This is basically what we're gonna be testing here. And if we do body, all right. So if we do code gen on this, or IR gen on this, what I've done is I've just generated the body of the try and not the catch. And so what we should see is, just the throw, right? So we have an entry block, and then we have the throw inside. And what I'm going to do here is we're just going to, wait, where did that go? Give me this. We're going to end up with a try block. This will be like try 0. And then our, this will probably just be, this will be kind of like this. Our entry block is going to jump into our try block, and we'll just have a dedicated try block. We can worry about like merging these later. Like we'll have a separate optimization pass that when it's doing dead code optimization, dead code removal, can also merge blocks as needed. So our try is going to do a throw. We're also gonna need to be able to represent catches. So we're gonna have some sort of catch. Yeah, how do we want to do this? LOVMIR is quite complex, the way that it does these with landing pads and invoke. I think we could simplify it, because we care more about the higher level, and we still want to keep enough information to where it makes code gen easy, because we don't want to go so low level that it becomes harder to do code gen for this. Yeah, I kind of want to look, so LLVM IR. And we have landing pad. So LLVM has this it has a landing pad. It also has a catch pad. I need to remind myself of the difference here. Landing pad is used by exception handling system to specify that a basic block is a landing pad, one where the exception lands and corresponds to the code found in the catch portion of a try-catch sequence. It defines values supplied by the personality function, blah, blah, blah. The result val has the type result type. And then catch pad is you specify a basic block that begins a catch handler, one where, yeah, so I think the catch happens first, and then you have to then dispatch to the correct like landing pad. This is it's so low level. It's so bits and bobs. I think that we don't want to be this low level in our IR. You know, if I stop saying our IR, if I say Jank's IR, then I don't have to struggle with saying our IR, which is so difficult to say. I should just say Jank's IR. Then there's also how this all comes together is with invoke. And do we have an invoke here? No. Invoke, and I can't click on that one. This one's underlined. So invoke takes invoke tells you where to continue to, like a different block to continue to, and where to unwind to if an exception happens. And so you have to do this on a per call basis with LLVMIR. I wanted to do this at a higher level. So how do we represent this? We might just end up coming up with our own thing here. Which I think is acceptable. What are the main things that we need to do? We need to convey that we need to convey when a try starts. So if we did something like this, try and then we also need to convey our catch points. And so I think all that would go in the try as well. And so our catch points would be catches. I'd probably just make this a map. Does the order matter? Does the order matter? Yes, they are tried in order of appearance. Which means we can't use a map, we have to use a vector. And we'll just use pairs. So type, this will be the type that we're actually catching. And so this will be something like jank runtime object ref. And then the block will be catch one. And then we need to merge all of these together. So we need another merge block. And so this will be, I don't know, numbers don't fucking matter there, but basically we're going to need to do like a find node in order to set a value inside of the try or any of the catches, which then is going to be the resulting value of the try. We're also going to need a finally, which we would specify here. But I think we only specify it if we have one. Right now we don't have one. Okay. I see the rough structure. And I imagine that this does not make sense because I haven't actually filled in all of this yet. But bear with me because this will make sense. Actually, I don't know if it'll make sense to you, but it might. Okay, so first thing we need to do, we need to we assume that we're in some existing block, like entry block. We need to create a new block. So what we're going to do is we're going to say auto try block. And we're going to make a new block and next ident, and we're going to call that try. And then we need to generate a jump to that try block. And so that's what we have right here. Inside of our entry, we have a jump to our try block. Okay. So we make a try block that adds it to the list of blocks. Then we create a jump to that try block. Done. And now we've done this, and we've created this block. Now we need to create a try instruction. That try instruction needs to have the catches. It needs to have the finally, and then we just need to deal with stitching everything together. So let's do this. Let's make a try instruction. We have a throw one, so I'm gonna make the try one right near that. I'll probably go above that. So try, and the way that this is gonna work is we've modeled it out here. We have our catches, which is gonna be a vector of types and blocks. So we could do a pair there. Hey, Dave Lightman, welcome to the stream. I hope you're doing great. I need a vector. So I think we could do a pair, and we need this is our type, and then this is our So we have our catches, and that'll just be our value. And let's not worry about finally yet. We're just going to simplify this, and we're not going to worry about finally yet. So give me this, there, catches. And is there more that we need here? Nope, the type of that is void, has a name. Yeah. Yep. Cool. So let's just do this. And then, wait, we want to go into here so that we can define this. And we want to do one of these. And we're just going to grab this. And this is going to be catches. And JTL move catches. Okay, that's that. There's our constructor for try. Now we just need to add a print for that. We're gonna need a loop, so I'm just gonna grab one of these guys and try. And so this guy is gonna be called try, and then we're gonna have catches, and we're gonna go through catches, and this is gonna be called catch. And inside of here, what we're going to do is we're going to need to print the type and the block. So let's do this and this. So we'll do type and block like so. And then we'll get the qualified type name, which is going to be catch first, and then the block is going to be catch.second, and that's it. That's the printing for try. Now inside of the builder, we will extend our builder API to have try. Try is going to need to take all of those catches. We'll do that by our value catches, and then we'll jump into here, bring that in, builder. And so here, all we need to do is just construct one of these. Try, we'll have our name, we'll have catches. And that is, that's that. So all right, so now we have all that compiling. Now the only thing that we need to do is, well, let's see what we have now. Unresolved symbol. What is unresolved symbol? Why is this unresolved symbol? Oh, because in jank, I actually have all of this, like so. So like this, the jank was actually like on line 7 of that file trying to compile all of this code, and that didn't make sense. Okay, so yeah, so we do our jump. And then right now we're adding stuff after that, which doesn't make any sense. And that's okay, because what we need to do is we just need to enter this block and start adding our stuff there. And so what we're going to do is we create our jump. So we create a new block right here, and then we create a jump in our current block to the new block. And then we need to just enter that block. And so this allows us to start adding instructions to that block. The builder just keeps track of which block it's in, and then whenever you add instructions, it just appends them to the end of the block. Cool. So now we can see that the literal and the throw that we had here were added to our try block. Now, before, and the literal and the throw came from the body of the try. Now, when we enter our block here, we then need to do a try. And when we do a try, it's gonna want all of our catches. Let's just not give any catches for now. And so we're gonna be able to see our try, we're gonna be able to see our try instruction show up as our first instruction of the try block. We should be able to run this now. Cool. So here we have our try instruction. We don't have any catches set up right now. And so now all we need to do is, before we create our try instruction, but after we enter that block, actually, we don't really need to enter that block yet because we're not creating the try instruction yet. So let's just loop through all of our catches. So we have catch bodies, auto const catch in catch bodies. And let me just jump to the, so we have a catch here. A catch has a type. It has a symbol for the value that is going to be represented. And then we have a do ref. So we have a do for the actual body there. Cool. So all we need here for each of these catches, we're going to need to make a new block. And we're going to need to keep track of all of those. So we're going to have a SD pair of pointer to void. That's our type. And then identifier. That is our block name. And so I have catch blocks like so. What did I miss here? There. And so we could do a catch blocks, expr catch bodies, size. It's really not neat. It's just habit. It's just a habit to always reserve, you know, like whether or not the catch blocks vector is reserved here is not going to impact compile times, but it's old habits. So now for each of the catches, we're going to need to generate a block. So we could do this, and we'll have a catch block, and it'll be prefixed with catch. And then we're going to need to enter that block, and we're going to need to generate our body into that block. And so we're not generating any jumps to that block or anything like that right now. All we are doing is just entering it. And so enter catch block. And now we're going to do a gen. Yeah. We'll do a gen of catch. And this has a body right here. And B. And now we're going to hang on to this. And I'm just going to mark it as unused for now, but I think we're going to use that later. And then we're also going to do a catch blocks in place back of two things. So we're going to need the catch type, which we have here. And then Oh, the blocks are not actually an identifier. The blocks are going to be a... The blocks are going to be... When we branch, we do store identifiers here. Okay. We probably want a helper to be able to do that. How are we... So when we do a branch... Yeah, right now I'm actually reaching into the blocks and grabbing their name like this. We should actually have a helper in the builder to do identifier block name given a use size const block index like so. Did that? Oh, that goes underneath. And so here we're going to return function blocks block index name. Okay, and so here we could actually do block name and then whoops, and then that, and then similarly we could do this and that, and then block name, and then that. And then was there effing blocks? Cool, we're not doing that anywhere else. So we can actually do that here as well. So we'll just do block name of catch block, and then we'll get the identifier for that. And then here we could do a move of catch blocks. Let's see how all of this comes together, if it does or if it does not. It does, comes together. Compiles and links. Cool, so fails at runtime. It fails because we do an unwrap right here, and we are at 109. What's it, 109? Right here. What are we? What if we just do one here instead of a throw? Okay, so it's not that. $466. So we're here. That's 466, and then 50. Oh, that's visit 54, 466, and then 296 is we're doing our do. $378 right here. So we're generating our catch body. We're generating our catch body, and we end up, so we have gen for try right here, and then we end up doing gen for do, which is going to be this, and we fail We have a call. This is at 466. Wait, 466. Right here, we're in for call. We can see call. But then when we get into gen for call at 109, one of the arguments does not give us a value back. So right here, it would be this E. I see. So we can see that we're in a try, like we're doing gen for try, then we do gen for catch, then we do gen for the body of the catch, then we're in a call, and one of the arguments, which is how I ended up arriving at it being the E here, just from reading the stack trace. Why is E not found? Yeah, we need to, I think when we generate the body of the catch, we need to add the symbol for this guy. We need to add this into we need some way to access this, because right now we're trying to look it up as a local and it's not there. All right. I don't know yet. So we're just going to leave a to-do, add exception value to scope. And then aside from that, we changed what we're doing here so that we just print caught instead. Let's throw here. And then all of this should still come together. So let's see what we have. We have our entry. We jump to our try. We have catches. This needs to be in quotes, but aside from that is fine. Yep, our catch block is catch 2, and we're catching a reference to object ref, which is correct. Then we grab literal 1, and then right now we return. But we just updated this to throw instead, so now that we've compiled that, we throw. Yep, so now we grab a literal 1, and then we throw. And now catch 2 is going to take the literal caught. It's going to grab print line, deref it, dynamic call, and then we're going to print the result of that, and we're going to return. Okay. So this is fine. Because we're in tail position, the return works fine here. But if we're not in tail position, then we're going to need to have a shadow variable in order to get the result out of this. So let's fix the print for this, because the types here need to go in quotes like so. That's easy enough. That way this will be quoted. And catches is fine. Okay, so we have two things that we still need to sort out. One is we need access to that that E value. We need access to the exception value. And we need some way to get access to that. I don't know if we want a dedicated instruction to just access the exception value. or if we should use some sort of shadow for that. I don't think that we should use the shadow variable for that with the phi epsilon, because when it comes to validating, we're not actually going to have a epsilon for it. Like, we're not going to have a branch set which sets a value for that shadow variable, and this would make it harder to validate that the IR is correct. Right now, we don't actually have IR validation for Jank's IR, but we're going to have a very thorough validation pass that's going to go through every instruction, every block. It's going to assert dominance, which is the official term when it comes to these instructions and the ordering of the instructions, and also going to ensure that, you know, all of the identifiers that are referenced exist and everything like that, that all of the types are valid and so on. And I think if we have a shadow, like if we have a phi without an epsilon, I think that would be a difficult thing to, like, it would be an edge case for exception handling, which I don't want to have. So instead, I think we probably should just, like we have an instruction for getting parameters, we should just, can we use the parameter instruction? No. No, we can't. Not without like being ambiguous in some way. So yeah, we need a new instruction. We need a new instruction for try, which is going to be, like, the goal here is to get the value out. And so maybe, like, you know, we could call it like exception value or get exception value or whatever, but maybe we should just call it catch, because that's basically what this corresponds to. You know, like, we'll have one of these per catch at the top. So we have a try at the top of the try block, and then we'll have a catch at the top of each catch block. And then its goal is to pull out the exception value and put that into a thing. I think that makes perfect sense. So let's just do that. So we'll get a catch, and a catch is going to, it's just going to have a name, and it's just going to have a type. And so we don't actually need any other data there. And let me grab this and then jump into this and then come down here. And so we'll just do this, and actually we'll just do that. Cool. Now we need to be able to print it. Printing it should be straightforward. We're just going to do throw. We're just going to do catch. Doesn't have a value, just has a type. Yeah, that's it. And so we add that to the builder. And so we have catch, and this takes in a type just like this guy. Whoops. And there we go. And here, and here. And I'll probably just grab this guy. And ret catch value. Wait, no, this doesn't take a value. This just takes a type. So for this, catch, bam, type, name. Yep, name and type. That's that. Good. And so then inside of each catch block, when we enter the catch block, the first thing that we do, so let me delete this because we're working on that now, is that we do a catch, and then the type is the catch type, like so. That's going to give us our local. And so then what we do is I don't know if we want a better way of doing this right now, but this will work. So we need to register a local. Locals are identified by their name, and so we have a catch. This has a sim, and we just have a get name on that guy, and so we can just assign like so. So now that local will be available. And so then when we do the gen on that, we'll be able to access it. Yeah. So now if we jump into here and we add our E, we should hopefully be able to grab that. This is complaining because I didn't add this to builder. Great. So all that compiles. And let's see how it runs. Okay, so in our entry block, we jump to our try block. In our try block, we say, okay, we're now in a try, and we have this catch here, catch block 2 for this type. Then we throw 1. Now in our catch block, we say, okay, we're in a catch for this exception type, and that gives us this v3, and v3 is our E at this point. So this is there's an implicit ref here, which is why you'll notice that this is a reference right here, even though we didn't actually write out reference here. And so E ends up being v3. Now we grab the literal cot right here, which is a keyword. We deref println, and then we call println with cot, which is v4, and v3, which is our catch. Fuck yeah. And then we return the result of println, which is v6. Cool. So everything here is correct. Now we have a way to encode try and catch in our SSA. And the only other thing that we need to deal with is, which is a little hairy to be fair, we need to deal with the merging of paths when we're not in tail position. So let's do something like this. Right? Yeah. So this is a problem here. So when I take this try and I move it out of tail position, so it's not in, like, it's not going to be the return value of the function, which you actually notice there can be an optimization done here where, since this is the only value and then that value is being used in return position, then we could actually put this in return position, but we don't do that right now. But when we see this, hey Lambda X Prime, welcome. Hope you're doing great. We end up generating a return inside of our try. Yeah, but we already have a throw, and our throw. So we have a couple of issues here. Like one is that we're not checking if there's already a terminator, and so we're creating another terminator here. And so now we have two terminators in this block, and that is invalid. That just violates like one of the SSA principles. The second issue is we don't have a terminator in our catch 2 block, right? So what happens if we end up in our catch? Okay, so we do a try, we do our throw here, we end up in our catch. So we do our catch operation to get our value, we do our print line in order to say, yep, we caught this value. Then what do? What comes next? This is where the merging of operations needs to come in. So let's handle the merging of operations before we handle the cleanup of extra terminators. And the way that we do this is we're going to need to check if we're in tail position or not. So we go into our try, we generate our body, and autoconst, and let's say try res, and this also, let's say, is maybe unused for now because I don't know if I'm going to be using that just yet, but I think we're going to want to. And now we do this for ifs already. So we're going to do largely the same thing. I just want to check. Yeah, we check in 3 places. Yeah. So here we're going to need to check if we need a merge block. Here we actually create the merge block regardless. And then we remove it at the end. When we remove a block, do we update the index of all of the subsequent blocks? We do. Okay, so I've already covered that. Yeah, okay, so in order to do this, where were we? Right here. We're gonna need to make a merge block, and we're gonna need to make that merge block up here. So we need to merge. This merge block is basically where all of the paths are going to go. And so if you imagine that we have this try block, and then I don't know, maybe we have 1 or 2 or 3 different catch blocks, and they're not in tail position. That means that when they're all done, they all need to end up going into one block. That is the next block that they're all going to continue from. And that is going to be the merge block. And in the case that we are in tail position, we don't use the merge block at all because the try block and the catch blocks themselves will already just return. But if we're not in tail position, then we need to manage that ourselves. And so here we're going to say if expr position does not equal analyze expression position tail. If we're not in tail position, and we're currently in the catch block right here because we entered it right here, and then we generated our catch instruction, and then we generated the body of our catch. So we've already done the body of our catch. Now, if we're not in tail position, that means that we're not going to have a return instruction. And so now we need to do a jump. So we need to do a jump into the merge block. Now there's more that we're going to need to do before this. This is where our upsilon comes in. But for now, we're just going to tie them together with a jump. And then similarly, we're going to do our try. When we're in our try block, we're going to do our try, and then we're going to do our try body. And then just the same, if we're not in tail position, then we're going to do a jump to the merge block. And then I think what we could also do in here, same thing, is that we could actually just start filling in the merge block. So if we do an enter of the merge block, so that way the instructions that we start creating are appended here. How are we going to return? Yeah, so here we return try res. And now that's used. And then here we return, we're actually going to return the last thing of the merge block, which we don't have yet. Okay. Enter the merge block, and then what are we doing in our merge block? Nothing yet. Nothing yet. So we have a to-do to bring all that together with a phi node, basically, but we're not going to do that just yet because we haven't done the upsilon either. Okay. Why is the merge block put in front of the catch block? It doesn't actually matter, but it doesn't make sense to me. Oh yes, because we added it right here. Hey, Johnny, how does Jank implement a garbage collector? We didn't implement our own garbage collector. Jank uses an off-the-shelf garbage collector called Boehm. It is BDWGC. And Boehm is this existing conservative garbage collector that's been around for like over a decade, maybe even two, that's written in C. It's used by a lot of projects. So it's a temporary solution for us, but it works. The long-term plan will be to use a tighter integration for a more precise GC. If you want to, I mean, since you're doing research on this, if you want to know what we'll be using in the future, we'll be using MMTK. MMTK is a Rust like garbage collection toolkit that is, it's not specific to Rust, but it's written in Rust, and it's a set of garbage collectors. And when you integrate with MMTK, you can then swap in and out different garbage collectors as opposed to integrating with just one. And that is the research that they've been doing from MTK and the garbage collectors that they do have are competitive against JVM's garbage collectors. In some cases, can beat them as well. I'm not a garbage collection expert. I just know. I don't have the details. You can go read the white papers because they've published them. But it's a much bigger integration to bring in something like MMTK compared to BOEM. Hey, PeaceMice2K, what do you use to highlight the current block? Do you mean this vertical highlighting here? This is a NeoVim plugin. Let's see. I think it is. Let me look it up here. Let me indent scope. I think it is. Is this the one? Is it going to play? Go, 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 go. Yeah. So this is the same thing where it's showing it here. This is all fucking fancy and animated and shit. I don't have like animation or anything, but hopefully that sets you down the right path. I've been struggling to write my own tiny GC. It's not really that simple to be able to run it from anywhere if needed. I always need to keep track of locals, etc. I eventually simplified it to run after every repo evaluation, which is bad if the one evaluation is expensive. Yeah, doing your own GC is I think certainly doable if you don't care about it being like super fast. If you want it to be, if it builds character, man, yeah, it does. I think it's a good exercise if you are not trying to go for something that's super fast. If you're trying to go for something that's super fast and also build a language, then it's probably too much. Probably too much. Why is this not indented? Why is this indented in a weird way? That's so weird. GC handbook worth a read. I haven't actually read that, but I do have it. It's on my list. It's on my list. Okay, so I haven't read many programming related books in the last decade. Reading's been my like escape. I just read fiction. Okay, right. So yeah, the merge block was created above the catch, which is fine. I just don't like it visually. I just don't like it visually. I kind of wonder if I want to like delay the creation of the merge block to put it after because it's visually easier to understand. But I don't know if it's worth complicating the code for that reason. I don't know if, yeah, I mean, we're gonna get to a point where blocks are complicated enough to where like you're just not reading top down anyway. So for now, I'll just do it to do. Okay, so in that case, we jump into our try. We have our try instruction. We grab the literal one. We throw it. Again, we have a jump here because we're not yet doing a terminator check. And that is what we can do right now. So we can say if we're not in tail position and B current block has terminator. So if we're not in tail position and our current block does not have a terminator, then we can do a jump. Wait, why do I still see the jump? Throw has terminator. Oh, because this is in the catch. What I want is actually right here. Right. And so then for this, that is when we do this. We separate these. Hey, Lysek, how's it going? Okay, cool. So now we do our throw. We don't do a jump after that. So we do our catch. We grab our literal caught. We do a print line with that. We jump to merge two. Perfect. And then here we do a return. The problem is the value that we're returning, we're not actually passing values yet from the catch into the merge. Working on a small display manager lately. That's cool. How am I doing? I'm doing great. I'm working on an IR. Okay, cool. So now we're gonna do these. Epsilon and phi. So before we do our jump, we're gonna need to have a shadow variable, and so auto const shadow, and this is gonna be next shadow. Closure's fun, LLVM's fun, C++ okay, second pulse are not fun. Yeah. So here we're going to do a branch set, which is our epsilon. We're going to grab a shadow, and then we're going to do the catch res, and this is where we end up using this from. And we're going to do an unwrap on that because that is currently an option. And then here where we need to do epsilon as well, we're going to do the same thing, but on try-res. Perfect. And then here we're going to do a branch get, and that is going to be our shadow, and that is what we're going to return in that case. And this, why prevents automatic move? Fine. And then what's wrong with this? Too many arguments. Branch get takes a type. What is the type of this? This is just going to be untyped ref. How does jank implement exceptions similar to jank uses C++ exceptions. Jank is a C++ dialect. Okay. So now we have our value propagation properly handled. Let's try this without a throw, and I'll show you what I mean. So success and failure. Okay, so what we do here is we try, and if we succeed in our try, we get success. And if we fail by catching something, then we get failure. And so what we can see here is we have our entry, we jump into our try. And so here's our try block. And so we say, okay, so we're in a try. These are our catches. And so we just have this one catch 4 that's catching reference to object ref. And what we do here is, because our try is going to succeed, like we can just sort of, we can tell that by looking at it. There's nothing here that's going to throw. We grab the literal success, which is a keyword. Now we set that. Here we do our upsilon. So we take value 10, which is our success. We set this shadow variable S3 with that, and then we jump into our merge block. And so here's our merge block. Now we do our branch get, which is our phi. Here's our shadow variable that we set here. And so this is our success. And then we just end up returning this. Now we have type erased our shadow variable here to object ref, which I think we have to do anyway. And then we can just return that. Now, if we had thrown, like let's say we call a function here that maybe throws, like I think we'll get an error here because this, yeah, that expects a string. So this would throw if you ran it, because subs expects a string and not nil. But it's not a terminator. It's not a terminator like throw is. And so we're going to generate the call to it. We have our literal nil. We have our literal 5. We get subs here. We do a deref of it. We do a dynamic call, and we give it nil and we give it 5. And then we try to grab success and everything like this. Okay, but this is gonna throw right here. And so we're gonna end up in our catch. We're gonna grab our exception value out. We're not actually gonna use this, so this will be dead code, which we can remove. We're gonna grab our literal failure. We're gonna set v6, which is our literal failure here. We're gonna set that into our shadow variable. And then we're gonna jump into our merge block. We're gonna grab our shadow variable. We're gonna return it. Nice. What does the throw look like? If we were to throw, let's say we throw success here instead. Then we have a throw right here. So we grab the value and then we throw it. If you put things after the throw, yeah, so if you put things after the throw, we should not actually generate these. And so this is a problem because throw is considered a terminator for the block. Yeah, we need to figure out how we're going to handle that. Throw is considered a terminator, which means having stuff after this throw is not valid. But having stuff after the throw doesn't matter. Like, all that is dead code anyway. So maybe we remove that. I don't know if we remove it during analysis or if we just don't, or if we don't generate it. Yeah, we'll need to figure that out. So throw ref. Yeah, I don't know how we're going to handle that. Accidental bug reports. Yeah, for sure. But I mean, that's not, it's not so much a problem with throw. It's just a problem with like another case we need to handle. But yeah, if we do throw here, so let's say if we did this, if we throw success and then you grab E and then you evaluate, so that way catch returns success, then res will end up being success here. So we can see the propagation here of the value. So we enter our try, we grab the literal success into V9, we throw it, V9 here, we'll catch it right here. So we'll catch it, it's type erased because we're just catching it by object ref. And then we, that goes into, so this is our E, our exception. We put that into our shadow variable S3, we merge, and then we grab our shadow variable and we return that. Hey, Air Search Engineer, welcome to the channel. Hope you're doing great. Okay, let's try. How do we do the throw? How do we not generate after the throw? Is that something we care about right now? I don't know if that's something that we care about right now, because I don't know if it's something I want to handle in analysis. What does Clang do? So if we go to Godbolt, there's no reason to bother with it right now. Well, I mean, it needs to be done eventually. It needs to be done eventually. So if we throw 5 here and then we, let's see, we have the vector header. So let's say we do a push back 5. So we alloc the exception and then we throw, and then the IR of course has nothing, or this is not IR, this is assembly. So let's get the actual IR here. Where is my, I just have to figure out tool. Oh my God, it's one of these things. Control flow graph. Don't quite want that. Oh, it's because I'm using GCC. Clang. If we do this. Now here, I should be able to do IR, yes. And this is going to go up here. And so, yeah, and so in the IR for this, so this is LLVM IR. That's generated from this C++ code, just so you know. We can see here that we define this function foo. We actually alloc space for the vector. Like this was reordered to alloc space for the vector first, and then allocate the exception and then throw the exception. But the pushback never happens. We can see here there's no call to pushback. But that's only because there are no optimizations. If I were to enable like O2, we can see here that there's actually no vector allocated here now. Right now, it's just the exception, and so that's just because no optimizations are enabled. No, you don't have to. I mean, as we can see, when the optimizations, I think probably even O1, yeah, even with O1, there's no vector here. And that's just because the C++ compiler will know that creating a vector and pushing back something doesn't do anything. So there's no reason to have that. So I don't know where Clang handles this. Like, one thing we could do is just check whenever we're adding, if we already have a terminator, and then just don't add any more. Yeah. I want to look into the pros and cons of doing this of like prepping this in the AST versus doing this right now in IRGen. Not sure. That could end up badly though, in terms of not reporting the proper issue. What do you mean proper issue? None of this affects like behavior. You know, like, for example, you still need to have valid code after a throw. And the same thing is the same thing would be true in closure. Like, if you just did like blah, blah, blah here, like, that's not valid. This still needs to be valid code. But so we'll still analyze it, but we'll also then remove it. So it needs to be valid code, even though it's never going to run. And that's just how these things work. And like, it may sound like, oh, well, that's so silly, that's never actually going to happen. But like, especially with macros or something like that, you may very well end up with some code that ends up after a throw where you're just like, yeah, that's fine. That's just, you know, the way that I want it to work. And you don't want that to be a problem. Okay, moving on. So yeah, we'll leave that as is for now. I have a to-do for that right here. I also have a to-do for potentially merging the or creating the merge block lower, but I'm not too concerned about that. Let's see, what time is it? 5. Okay, so I think that we'll do one more. We'll do one more, which is case. And case is another pretty interesting one where we're going to be making a whole bunch of different blocks, because each branch of the case is going to end up needing to be its own block. So how is that going to work? Yeah, I think we would probably just have a case instruction. So if we jump back into here again, and we let's say we get rid of this. We're going to want to try. So let's say we have a case. We're probably going to want something like switches, and this can just be a map. And then the way that case always works is that these switches are just hashes. And so we'll have an integral value, like 53, and then we'll have a block. And so we'll have like case 0, and then we'll have another integer value, and then we'll have case 1. And we're gonna need, the other thing that we need is we need a value for the actual thing that we're gonna be doing a case on. And so this would be something like a name, v0, and then like a literal. Let's just say something like this. Reading the Clojure source code of case makes you uncomfortable. Yeah, cases, the case macro actually handles a lot of the work. And then when it comes to the implementation, because like case is a macro, and then it's backed by a special form, which is case star. And case star is a much simpler thing. So we can see the C++ code gen for this ends up being, well, I guess it's easy for me to read, but that's only because I wrote it. And I'm familiar with the way that we're doing C++ code gen here. So it's going to be relatively straightforward because the macro handles so much stuff for us and then just sets us up basically with integer values. I think. So let's just do, it's branch related. So let's do a case under branch. Case, and case is a keyword. In C++. So we need to call it that. And then I'm losing my voice. And so we're going to need, actually, we'll keep this. We're going to need the value. And then we're going to need a native, let's just say native unordered map of I64 to identifier. And that is going to be our cases, I think. Yeah, makes sense. So we're going to grab this. We're going to come down here. We'll do this cases. We'll remove these. We'll remove this. And then this will be the value. And I'm so happy that I'll never touch code gen Lamau. Yeah, it depends how you're doing code gen. When you're generating like another source language, it's really not bad. It's actually pretty cool. Like generating C, for example, is a pretty smart bet because you can get a lot of compatibility, like a lot of portability, compiles really quickly, and so on. Okay. So case is going to have, case just have a void type? I think so. Case just has a void type. And so we're going to have cases. And so that'll be a move. And then we'll have also value, which is just value. And that is it for case. And then we need to handle printing of case. And so I will probably just grab, one of these guys. And then where was branch? Here. And so this will be case, And here's case. And now we have value. And then we have, let's say, cases. And so we have name and value. Don't get me wrong, it's super cool, but my head just can't wrap around. Yeah. And okay, so here we have cases, and we'll just call that C for now. And what we have for those cases, it's I64 an identifier. And so we are actually going to need to do something along the lines of this right here. And so we'll say value, and that'll be that. And so that will be C first, and then block is actually, that's right. And so that's C as well. Yes. And then branch. So here is case. And then we can just grab this unordered map here. That's what we're going to be bringing in right there. That is going to be our cases. And then we're also going to have an identifier right here for our value. It's going to be a ref to const. And that's it there. So now if we jump to here, to the bottom, we put this inside of builder. And then we're just going to, I think we can just take this. So we have a name, type is handled for us. And so then we just do value, and then we move in cases like so, and we build a case here. Okay. That was a lot saved all at once. Welcome back, Broad Checker. Cool. So now we have a linker error, and the linker error is for vtable for case, which is referenced inside the constructor for case. Why is the vtable for case? Name value cases. It's because of that. So yeah, we had overridden, we had marked a function as overridden that we didn't actually end up overwriting. And that changed how the vtable was generated, which then led to a linker error for the vtable, instead of just saying that that member function was not implemented, even though it was marked as being overridden. So deceptive errors from our friendly C++ compiler. Cool. So we're just going to comment that out for now. And then we are going to, we're going to do our case here. So let's do a case on 5. And we'll just do something like this to start with. Cool. So here we're grabbing 5, we're grabbing nil, and then we're returning nil. Because for the case, we're not actually doing any code gen for this yet. But let me get some more water, and I'll be right back. Stay hydrated. All right. So we have provided everything that we need in order to actually do this case generation, or at least create the case instruction for now. So case, here we go. And then we'll have a bunch of cases here, and we can start off by, so we'll get our value, value ident, and that is going to be a call to gen with value. And then we'll do that. I think we're probably going to need to take in the expression position. Mm-hmm. Cool. So we grab the literal 5, that's v0. We do a case with the value of v0. Here are our cases. We haven't done those yet. And then we have a ret. Yeah, so this is going to need, it's going to need the position as well, because you, you can have a case in return position, and we're going to need to be able to generate that appropriately. Is that right? Is that right? I don't know. I don't actually know. Maybe not. We'll hold off. We'll hold off for now. We'll see. So with the case, we have our value that we're actually going to do the case on. And then we have a bunch of different cases. And those cases we're representing as right here a map of the hash, which is actually not, it's not I64, it's U hash. So let me change that here as well. And jump back down into here, U hash. And so we have our cases here. And now we're just going to loop through. Let's see. So we want to loop through keys. Oh, look, there's a to-do that says that that should be uhash. Yeah, so let's see what we do here. We loop through our keys. We do a case on all of those. I actually don't know if that's uhash or not. But the keys right now is I64, so let's actually just undo. So let's match this with the keys for now. So we loop through all the keys. We do a case on those. We do the body. We do a break. We do a default. We have our default, blah, blah, blah. And that's about it. And that's about it. Yeah. So we'll make a block, and then we will enter the block. Do we need to enter the block? Yeah, we'll enter the block, because we need to generate the body of the yeah, and that's expers. So we have keys and expers. So we need to actually loop through both of these. We can't actually use a range-based for loop. So we need to do a usize I is less than exper keys size, and we will know that exper keys and exper what is it? Expers? Yeah. Those are going to be the same size. And so we enter that, and then we do a gen. We do a gen of expers sub I b. That's going to generate our block. And then also we do a cases sub exper keys sub I is equal to and block. That's equal to our block. And then right here, now we have our cases. We can move our cases in. Why doesn't this work? No viable overload. Block name. Yeah. Okay, so this will generate, go through all of our cases. It will generate a new block for each of them. And it will fill in the block with the expression that's in there. And now, yeah, we can take a look at what we have, but we know that we need to do some work for, if we're not in return position, if we're not in tail position, then we're not going to have terminators for these blocks. We're going to need to add. And so we're going to need to do that with some, with a find out, basically. But let's take a look. Oh, we have an interesting if and else going on here. Why is that? So case actually expands to an if else in this, like the case macro actually expands to an if else in this scenario, which is why we don't have the case instruction at all here. All we have is a check to see if this thing is equal to this thing. What if we do, I'm just curious, what if we do a, is it only because we have one condition? Yeah. So it's the same thing here. We just do one check. Okay, so 10 meh. Now we have a case. Now we have a case and if shit going on. So we actually have a lot, we have more than a screen's worth going on now because case is so involved. Let's take a look. So in our entry block here, we do a literal 5. Now we have an interesting thing going on here that I noticed before and then forgot about. We enter all of our case blocks here. So we create our blocks and then we enter the blocks and we push it on there. And then when we get to the end of this for loop, we're still in the last case block, but we don't want to be. We want to go back into whatever block we were in before. And so we need to actually we need to keep track of the starting block by just saying, give me the current block. And then when we're done generating our cases, we need to enter the block, starting block, starting block index. We should probably just have an overload for enter block that takes in a reference to a block. That way we don't need to grab index there. But I'm not going to worry about it until we actually start doing it more often. That's a problem. Why is that a problem? Oh, also, one thing that we forgot to do was remove the merge block in the case of the try being yeah, there we go. Okay, So we have an issue with entering this block, presumably, but let me just compile what we have there, and then I'll go into a debugger. Seems like Kuvi's not here anymore. Borrow checker. Whoop. Okay, so 271 is where we're failing. That's interesting. Is that the right file? IR builder 271. Right here. Creating case. Move cases. Value, move cases. And we do, yeah, what's block index here? Right, 5, 4, no, 6. I want to go the other way. Okay. So yeah, we have some undefined behavior. We grab a pointer. Yep. Why are we using current block? So I can tell you what's going on here. Current block. Okay, so that's why. So what we want, so what's going on here and why it's crashing is we're grabbing the current block, which is a pointer to the current block. Then we're adding all of our case blocks, and then we're trying to enter the previous block that we were at by index, by grabbing the index from the current block. Because when you enter a block, you just enter it by index. The problem is the pointer to the current block is no longer valid because the underlying array that stores all of the blocks has been reallocated. It's been reallocated because we added more catch blocks to it. And so this pointer is no longer valid. And so when we try to deref here, it's non-null. So it doesn't trigger it like a debug assert, but it's just undefined behavior. The solution here is to not persist pointers to blocks across changes to the underlying structure. So what we want is we want to get the current block index. There are some cases where we actually want to get a pointer to the current block, such as checking if the current block has a terminator. But here, the only thing that we care about is the index of the current block. And so we should do that. What's the difference between auto const and const auto? There's no difference. The people who use const on the left generally they don't understand or they don't care about the rules of const. But the thing is, in C++, so you can do like const int I, right? And so you can say constant I is 5. But if you have a pointer, right? This is we start entering a realm where we have problems. So borrow checker, what is this type, right? People would say, oh, this is a const int pointer because they want to read this left to right, but that's not what it is. First off, that's just wrong, right? This is C++ types should be read from the right to the left, and so P is a pointer to const int, and this works well if you put the const here. Now you might say, oh, that doesn't matter, that's stupid. But where it does matter is if you have another P here. This pointer for P is not const, which means we could actually say, okay, let's change it, right? But if you want to actually make the pointer itself const, you can, right? But How do you do that? Well, you have to put it to the right. Okay, so even if you were using const int, if you want to make the pointer itself const, you have to put it to the right. And so there are scenarios where you have to put const to the right and you can't put it to the left. Other scenarios like this include member functions, right? So when you have a member function that's const, it goes to the right and it affects what is to the left. And so it's the same thing here. And so if you wanted an actual const pointer to a const int, or a const pointer to a non-const int, then you can get that. But we put const to the right, so that way we're consistent always. So similarly, and this is one of my pet peeves, when people have like a, like they'll have like this sort of thing, they'll say, oh, it's a const int reference, which is not correct because references are always const. You can't change a reference. It's not a constant reference, it's a reference to const int. Const auto, const name, no, because both of those consts would do the same thing. I don't think that's valid. Yep. But anyway, so that's why, like, you will find I always put const to the right, and in the jank code base, we always put const to the right. Anybody who commits like const's got to go to the right, because I like consistency, and const being in the left sometimes sucks. Okay, so we needed to get the current block index, and that's what we're going to do. So we're going to add a new function for the current block index. Does that matter? Or should we just grab the current block and get the index from it? Yeah, we'll just grab the current block, get the index from it. Current block index, and then starting block. There we go. Consistency in C++ ballast entry. Well, I mean, when you get to control your C++ code base, then you can achieve, quite a bit of consistency. You can like with C++ being as flexible as it is, you can achieve a lot in terms of establishing a style and a feel for your C++ code base. Do I have an auto format config? Yeah. So part of the jank repo. So jank GitHub, you'll find that there's a .clang format file. This is what we use. It doesn't do all the things I want it to do. Like this is not the style how I would write it if I were not using Clang format, but it's okay. But yeah, like when you go to like this whole like is error, expect error, unwrap, like jank's usage of result types and option types are taken like right out of Rust. And so a lot of the code that we have in the C++, like in the jank compiler runtime, ends up feeling kind of Rust-like. And you can write all of those as templates, and that's because of the power of C++. Unfortunately, it's not Rust, but it's still like, the way I write C++ is going to be drastically different from the way that most people write C++. And that's just because I have my own way of writing it that I like to do, that works well for my brain, avoids common pitfalls and so on. Okay, so this gives us, here's an interesting one. I don't know if this actually works. Yeah, this doesn't work like this. So case needs to be If it's written like this, case needs to be a terminator. That is either going to jump to one of those blocks. We could do that. I don't know the drawbacks of that. It could be that there are drawbacks to that that I don't recognize yet. It's not a huge thing. Like, that's an easy thing to change if we want to change it. After all, like we, implemented case in an hour on stream. So it's not a huge thing. But where did my terminator go? So we're going to grab this, and then we're going to jump into here, and then we're going to define this for case. I'm going to override this to return true. And we don't need this. We'll get rid of that. And all that is going to do that should remove the red that we have here. So if case is a terminator, then case is going to end up branching to one of these blocks. We need to have a default block added there as well. Yeah, we're going to need a default block, which is probably going to be stored separately. So if we did default block, case blocks, I'm going to rename this to case blocks. Case blocks, and then identifier default block. Case blocks, identifier, default block, and case blocks, and default block. Okay. Now when we do a case here, we're going to need to specify the default block as well. Identifier constref default block. And here I'm going to do that. And then here we're going to do that. Okay. So default block we're going to add here. And B. So auto const default block is block, and next ident default, and then we're going to enter the block. Default block, and then we're going to generate expr default expr B. And then here we need block name, like so. I missed a comma right here. Looks like I didn't miss it anywhere else. Okay, and then yeah, printing needs to be updated because we still have cases. We need case blocks. We should probably just call this case blocks, like so, and then we should have a default here. Default block like so, and then default block. Cool. Now we compile and link. Nice. So here's our default added. Default 33. I don't actually see that here. So we'll have to see why that is. Here's where we add the block. We enter the block. We generate the block. And what's the default expression? Okay, that's just an expression ref. And then we enter a starting block. Where's our default block? Let me not generate any of this. And starting block. Yeah. Here's our default block. I didn't miss it before. Default 1. It just wasn't there before. Why? Not so sure. Generating the case blocks ends up affecting. So what if we generate the case blocks, but we don't generate the case block bodies? So we have our default here. I think that we have some indexing issue going on where we're like, maybe we're trying to remove a merge block, and because of the indexing, we actually end up removing a different block. Yeah. So if I generate here, we can verify this. And if that's right, I probably just need to come up with a different way of managing like I don't know, generational indices, some sort of like stable index. Yeah, so entry case one, if else merge case, if else merge. There's no default. Now, if we comment out this removal of merge blocks from the if, wait, this is from try. That's not going to affect anything. Right here, if we comment out this, I think we're going to end up with our default block back. In which case, maybe I can't remove blocks that way. Could always leave them and clean them up with like a dead code pass that detects for this sort of thing. Wait, no, I don't have my default here either. How many remove blocks are there? There's this one, there's this one. It's just these two. Everything else is adding blocks. We shouldn't hit this other one because that's only for try and we don't have try, but just in case. Entry case, if else merge case, if else merge. Fascinating. Fascinating. I hear you, borrowed checker. This one, we're probably going to need to step through with a debugger and figure out what's going on, because I'm not seeing how a block would be replaced or removed, or like why it wouldn't just be there. If we add a block, why would it not just be there? Now, I do wonder, just for my own curiosity, if we do the default block first before the catch blocks, does that change anything? Part of me, my gut tells me it will. My gut tells me I'll actually see the default block now. And I do. But I don't see the bottom. What? Is this a printing problem? Is it actually there? Yeah, this is a printing problem. Because here, we're closing the instruction, we're closing the instructions, we're closing the block, we're not closing the function. So the default block is there, but the printing highlight. So we use a library right now for this, and it has caused some fucking annoyances, and I think that this is one of them. Yeah, I want to rewrite all of this to not use this library. Fucking libraries. Okay, my default block is there, but I can't see it because it's not being printed. Because we have too much else going on. That is annoying. And then when we print here, we do fit the, we're supposed to fit the screen to the document, the height of the document. Fixed or full? Or fit? Fixed, full, fit. Extend beyond screen? False? True. No way. That's it? No, it's still not wrapped up. It is only doing one screen's worth though. Like if you look at the prompt is like 3 lines. 3 lines is what it is. It's doing above the screen here. So it's doing exactly one screen's worth. I don't know which of these is X and which one is Y. So maybe I should have changed both. But let me, now that I've changed both, let's try this again. Ah, wait, now there's default, but it's incomplete still. Ah! What? Ah, man. Damn. Raj, you want me to hire you? What am I going to hire you to do? Elevator pitch right now. I'm going to hire you to rest. That doesn't sound like a very good deal for me. Okay, so fit, I mean, this is fit the document, extend beyond the screen. No, I don't think so. I don't know what's up with this. I don't know what's up with this. Like, I think if I do fixed here and I give it some like, is this lines, I guess? What if I just give this like 100? Why is it still cut off? It's still cut off. Our documents are not allowed to be larger than the screen. Dimensions, full, fixed, create, render. Yeah, I don't know. I honestly, this might be the time where I need to rip this library out and just rewrite this highlighting, which is a shame because it's like, it's tangential to what I'm doing, but also like I need to see my output here. So anyway, on the flip side, we could, for now, since we know that this is a highlighting issue, we can just remove the highlighting and then print the whole fucking thing. Like, I don't know, just the whole like just print it to the screen, like from start to end, which is pretty crazy, I know. Showing the whole thing, whole enchilada. There we go. I don't know. Yeah, I thought this was a super cool library a year ago. And then when I started doing all of Jank's like fancy terminal output with it, I realized that it is not as cool as I thought it was going to be. This is interesting. Where does this error come from? Consider using the case macro instead of case directly. What? Do I have an error that says that? Consider using... No way, right? This must come from like the macro itself. Consider using... What? What is this? Where does this come from? Wait, I do have it here. Oh, this is inside of error analyze. Yeah, so the error comes from, like, there is a note added right here, but this note is added erroneously. We should be just pointing at meh here. What happens if you do this? This works fine. Yeah, so this is what it should do for the other case as well. Like, you know, we note that we're expanding a macro, fair, and then the issue is found here at meh. But when I put meh here in the branch, I should also just get an underline there. If I put it here... oh, that just ends up being a symbol, which is fine. Yeah, interesting. Okay, that's a bug. So unresolved symbol in case branch has incorrect error. Add that to the bottomless pit of to-dos, but we'll get there. It's not bottomless. There's a bottom. All right. Well, my highlighting is broken, and then that just frustrates me now. It just frustrates me now. So I kind of don't want to finish this case stuff because now I have to stare at this unhighlighted shit. Yeah. And now we're coming up on 6. Fuck it. Ugh. Libraries. Basically every library I've started with in jank that I brought in, I have ended up removing or like heavily modifying. I think that there's a lesson to be learned here. Starting with libraries, fair enough. It's a good move to like just use a library to get you going, but you will often just run into limits where you least expected them. And they may cost you a lot of time. Like here I was thinking like I had some indexing issue with blocks being moved around, everything like that, because my default block wasn't showing up. But there's no issue with my block management at all. It's a fucking highlighting library. Well, it's not a highlighting library, it's a terminal output library. But using it for highlighting. Damn. All right. So to recap, today we did a fuck ton. I mean, it's been 4 hours, but we've done quite a bit. So we did IR gen for list and vector and map and set. And then we did IR gen for try as well. And all of the bullshittery that involved. It's honestly not bad. When you look at it, like the actual gen here for try is less than 50 lines. Sure, we had to go create the instructions and then add, the printing for them. And then we had to register them with the builder so that we have a nice API for building these. But actually, like, I think that the API that we've built for IR gen, it's not bad. Like, allows us to be pretty expressive. Like 48 lines for try. If you compare that to the LLVM IR, it's like 700 lines to implement try catch in LLVM IR. and it took the guy who worked on it was one of my mentees. It took him several months, and that's not his fault. That's just because it's ridiculously complex. So this is the nicety that we get from working at a higher level, because we don't need to be so bits and bobs. And then we didn't get case done. We still have we were generating the case blocks. We got the code inside of those. We have the default block. We got the code inside of that, but we still need to tie everything together, and we make sure that. Like we'll need our phi epsilon stuff to make sure that when we're not in tail position, we end up with a merge block and everything goes together. And then we'll need to make sure that we handle tail position properly so that each of the cases ends up with a terminator. But we're not far off that. I'll probably end up taking some time, like on Friday or something, to just rewrite the highlighting stuff to not use that library. This is going to address some issues with the error reporting that we have now and the way that code snippets show there and the way that long error messages show, that I have some bugs reported for, because this library does like fucking word wrapping and stuff that I don't want, but I can't disable. So we'll go to just like straight up like terminal ASCII escape codes for outputting colors instead. That's gonna be better. That's gonna be better. Let's see who's online. If there's another fun like compiler dev person I can shoot you guys over to, then I'll do that. Oh, all right. That'll work. That'll work. I'm gonna send you guys over to more compiler dev. I hope you guys had a great time. I did. We got a lot done. I appreciate all of you. Have a good one, and I'll catch you next week. All right. Keep it cool.